Okay, so in this video I'm going to have a look at Leaving Cert Higher Level Maths Paper 2, 2017, and I'm just going to have a look at question 7. So this is question 7 here. It involves a cylinder with two solid cones fitting exactly inside it. So this is one cone here, the other cone here, and the two cones are welded here at their vertices. Now there's an empty space here. This white part here is the empty space in the cylinder. The cone and the cylinder, they both have radius large r. The cones have height r, and the height of the cylinder then is just going to be 2r. We have this sphere over here, this hollow sphere, which has radius r. We have to show that the capacity or the volume of the empty space in the cylinder, in other words this white part here, the volume of the empty space in the cylinder is equal to the capacity of the empty sphere of radius r. So in other words, the empty space in here should be equal to the volume of this sphere over here. So the way I'm going to do this is find the volume of the entire cylinder, find the volume of both cones, subtract them to give me the volume of the empty space. Then I'm going to find the volume of this sphere, and we should get the same answer. So let's start then. So we're going to find the volume of the cylinder first. So the volume of a cylinder is just pi r squared h. So in this case, pi, we're going to leave pi as pi, or the radius of our entire cylinder here is r, large r, which we're going to square, and the height of our cylinder here is 2r. So what we actually end up with here is 2 times r squared times r, so that's going to be, I'll put the 2 here, I'll put the pi next, and we'll have r cubed. And we're talking here about centimeters, so it's going to be centimeters cubed for volume. So that's the volume of our entire cylinder. So let's find the volume of our two cones then. Well, the volume of a cone is equal to a third the volume of a cylinder actually, so it's a third, the 1/3 pi r squared h. So in our case we've got 1/3, we've got pi. In our case our r here is large r, which we square, and then we've got our h here. The height of one of these cones is r, so it's just going to be r here. So we've got 1/3 pi r cubed, and again that's centimeters cubed. So that's the volume of one of our cones. We have two cones, so I'm just going to double this. So the volume of two cones is equal to 2/3 pi r cubed centimeters cubed. So that means the volume of empty space in the cylinder is equal to, it's going to be equal to this here, the volume of the entire cylinder, minus the volume of the two cones. So it's going to be 2 pi r cubed minus 2/3 pi r cubed. So 2 times pi r cubed minus 2/3 pi r cubed is just 1 1/3 pi r cubed, centimeters cubed. Now I'll just rearrange that fraction there. So we'll just call this 3/1/3. That's going to be 4/3 pi large r cubed centimeters cubed. So this is the volume of empty space in our cylinder up here. So now let's work out the volume of our sphere here. Well, the volume of a sphere is just 4/3 pi r cubed. Now in our case we have 4/3, we have pi. Now our r is large r cubed. So we can see here that the volume of empty space in the cylinder is equal to the volume of the sphere. You can see here that this value here is equal to this value here. So that's it for part A anyway, so let's move on to part B. this is part B here. Actually, I'm just going to move this up a little bit, just give me myself some room at the end. Just move it up just a little bit. Okay, so again we have our cylinder with our two cones in here, and we have our sphere here, but this time they've put some water in the sphere and the cylinder. Now you got to remember these two cones are solid, so this water is only going around the edge of this cone at the bottom here. So this time we're told that R is equal to 12. So the distance from here to here is 12. The distance from here to here is 12. The distance from here to here is 12. This is 12 here as well. So water is poured into both the cylinder and the sphere to a depth of 6 centimeters. So the water depth here is 6. The water depth here is 6 centimeters. Find AB first of all. So you got to find the distance from A to B here. This is the radius of the circular surface of the water in the sphere. So this is the surface of the water here, so we got to find this distance across here. Give your answer in the form A root B centimeters, where A and B are natural numbers. Okay, so let's just take this first. Now if you look at this here, really what we've got here is a right angle triangle here. So I can kind of join this up here if you like. Now if it's 6 centimeters from here, from the bottom of the sphere to A, it's going to be 6 centimeters from A to the center of the sphere, because this entire distance here is a radius. We know the radius here is 12, so it's going to be 6 centimeters here. So really this is just a simple case of Pythagoras' theorem. So if I just draw that triangle here, we've got something like this. We've got a right angle triangle here. This is 12 centimeters. This here is 6. This is A here. This is B. So we've got to find the distance from A to B. So we can write down 12 squared is equal to 6 squared plus the distance from A to B squared. So that will give me 12 squared is 144. 6 squared is 36, so I'm just going to bring that over, subtract. That'll give me AB squared here. So AB squared then is 144 minus 36, so that just gives me 108. So that will give me the distance from A to B then is the square root of 108, which is 6 root 3 centimeters. Okay, so now we have this little radius here from A to B. Okay, next we have to find CD. So again, let me just move this up a little bit. Okay, so we've got to find CD. So what's CD? Let's have a look at our diagram. Okay, so we've got to find the distance from C to D here in our cone here. Okay, so what I'm going to do here is just take this triangle here. So if you look at this triangle here and this triangle inside it, the little triangle inside it, CD will be parallel to this radius at the bottom here. So I'm just going to take this out and draw this, and then I'm going to split up these two triangles and use the fact that similar triangles, in similar triangles the sides are in proportion. So I'm just going to draw this triangle here first. Okay, so it looks like this, and we have C to D over here. So this is C, this is D here. Now we know that this distance here is going to be 6 centimeters from the bottom up to the top here. So that means from C up to the top here is also going to be 6 centimeters. We've got to find CD, and we know the distance along here is going to be 12 centimeters along here. Okay, so if I just split up those two triangles, I'll get something like this. So this is my large triangle, so that has height 12 and it has a radius 12 here. The little triangle will look like this. So that would be 6 here, and this is CD along here. So we know that these two triangles are similar because this is parallel to this here. So now I can just write down an equation where the sides are in proportion. So let's take CD here. So the distance CD divided by its corresponding side, which is 12, should be equal to 6 here over its corresponding side, 12. So if I just cross multiply here, I get 12 times CD, the distance from C to D, is equal to 6 times 12. So the distance from C to D then will just be 6 times 12 divided by 12. So that just gives me CD is equal to 6. The distance from C to D is just equal to 6 centimeters. Okay, so now we have the distance from C to D. Just to remind you exactly what that is, it's this distance here, is 6 centimeters as well. So we have this distance, this little radius here of this white circle, and we have this radius here as well. Okay, so let's have a look at the next question. So we've got to verify that the area of the surface of the water in the sphere is equal to the area of the surface of the water in the cylinder. So in other words, you see the circle here at the top is the surface of the water. We've got to verify that the area of that circle there is equal to the area of this water here. That's not including this white circle here, just the top of the water here, this blue part at the top here. So to find the area of this circle here is straightforward enough. That's just the area of a circle, and we know the radius here, so that's going to be easy enough. Here we've got a circle, we've got a white circle that we don't include in this big circle. So really the way I'm going to do this is find the area of the big circle, find the area of this little white circle, subtract them, and that will give me the area of the surface of the water here. And that should be equal to the area of this surface of water here. So let's start on, we'll start on this. This is easier here to do. So we're just going to do pi r squared. That's going to be the area of this circle here. So let's just work our way down here again. So we're just going to work on the sphere first of all. So the area of a circle is just pi r squared. So in our case we leave pi as pi, and in our case we found out that the radius, we worked that out as being 6 root 3. 6 root 3, so you've got to square that. So when you do that you get 108 pi centimeters squared, because we're talking about area. So let's look at the cylinder then. So in our cylinder then we've got two circles to look at. So first of all I'm going to get the area of the entire circle, the big circle, including the little circle as well. So again, area is equal to pi r squared. So in our case we leave pi as pi, or in this case is going to be 12. It's the radius of the cylinder is 12 squared. So that will just give me 144 pi centimeters squared. Now the area of this is the large circle, so the area of the small circle again is going to be pi r squared. So that's going to be pi times r squared, and we worked out r as being 6, so it's 6 squared, so that just gives me 36 pi centimeters squared. Okay, so in order to find the area, the surface area of the water then, so the surface area of the water then is just going to be equal to 144 pi minus 36 pi, and when you subtract those you get 108 pi centimeters squared, which, as you can see here, this is the area here of the surface area in the sphere, and this is the area of the surface area in the cylinder. So we can say here surface area of water in the sphere. Okay, so that's that bit done. Let's have a look at the last part of this question then, And this is to do with, let me see, the mathematician Cavalieri discovered that at the same depth the volume of water, so in the previous part of the question we were talking about surface areas being equal, now we're looking at the volume of water in the available space in the cylinder is equal to the volume of water in the sphere. So as I say, in the previous part of the question we were just looking at the two surface areas being equal, but now Cavalieri discovered that the volumes are actually the same as well. Now we've got to use this fact to find the volume of water in the sphere when the depth is 6 centimeters. So what we've got to do is find the volume of water in the cylinder, and that will give us the volume of water in the sphere. So what I'm going to do here is, let me just go back up here and have a look at this again. I'm going to find the volume of this cylinder here. If the cone wasn't in there, I'm going to find the volume of that. Then I'm going to find the volume of this part of the cone. I'm going to subtract the two, and that will give me the volume of water then around the edge. So I'm going to imagine this is just a cylinder here without a cone in it. I'm going to find that volume, find the volume of this thing here, this part of the cone here, which is called a frustum of the cone. It's just part of the cone. Subtract the two, and that'll give me the volume of water. That volume of water then will be equal to the volume of water here, which is what we were asked to find. So let's do that. Let's just draw this cone. First thing I'm going to do is find the volume of this frustum here of the cone, this part of the cone here, without this bit at the top. So let's just go back down again. I'll just draw it out first. So we have a cone. And here we've just got this part of the cone here that we want to find the volume of. Now there is a formula for doing this, defining the volume of this part of a cone in the tables, but I'm just going to do it a different way. I'm going to find the volume of the entire cone. I'm going to find the volume of this part of the cone that we don't need. I'm going to subtract the two, and that will give me the volume of this frustum here, this part of the cone here. So what do we know here? Well, we know that the height of this cone here is 6. We know that it's 6 from here to here as well. We know that our radius here is 12. So let's we know that this radius here is 6 as well. I think we worked that out earlier as well. Okay, so let's find the volume of the cone first of all, volume of the entire cone. This is the large cone, if you like. The volume of a cone is 1/3 pi r squared h. So in our case we've got 1/3, we've got pi, we've got a radius of 12 squared, and the height of this cone is actually 12 as well. So it's going to be 12. So when you work all of that out, you get 576 pi centimeters cubed, because we're talking volume here. So the volume of the small cone then, again is 1/3 pi r squared h. You may notice that I more often than not write down formula here. It's a good idea to write formula down whenever there is one. So we have 1/3 here, we have pi here. The radius of the small cone is 6, so it's 6 squared, and the height is also 6. So when you work this out, you get 72 pi centimeters cubed. Okay, so that means the volume of our frustum here, this part of the cone here, so the volume then of the part of the cone in water, if you like, is going to be equal to 576 pi minus 72 pi. So that just gives me 504 pi centimeters cubed. Okay, so we have the volume of this part of the cone that's in the water. So what I'm going to do now is find the volume of the cylinder. Find the volume of the cylinder that has water in it, if you like. So the volume of a cylinder is equal to pi r squared h. So again, in our case, pi is pi, r is 12, which we've got the square, and the water is to a depth of 6 centimeters. So this is going to be the volume of our cylinder of water. So it's going to be 864 pi centimeters cubed. Okay, so that means then that the volume of water in the cylinder is just going to be equal to 864 pi minus the volume of our frustum here, which is 504, and that just gives 360 pi centimeters cubed, and that's going to be equal to the volume, according to Cavalieri anyway, this is going to be the volume of water in the sphere. Okay, so that's it for question 7.